Assalamu alaikum warahmatullahi wabarakatuh, and hi. In this video we will look into the examples for Pelton turbine. Example number 1. A Pelton wheel is receiving water from a penstock with a gross head of 510 meters. One-third of the gross head is lost in friction in the penstock. The rate of flow through the nozzle fitted at the end of the penstock is 2.2 meter cube per second. The angle of deflection of the jet is 165 degrees. Determine number 1, the power given by jet to the runner. Number 2, hydraulic efficiency of the Pelton wheel. Take coefficient of velocity equal to 1.0, speed ratio equal to 0.45, water density equal to 1000 kg per meter cube. First of all, let us highlight the main information that we can extract from the question itself. The first one is the gross head, 510 meters, and then one-third of the gross head is lost in friction. And then the flow rate is equal to 2.2 meter cube per second, and the angle of deflection is equal to 165 degrees. It's a good practice to write down all those information. So we write down first the gross head, Hg equal 510 meters, and then the head lost in friction, which we can calculate from gross head, which is 510 over 3 equal 170 meters. And then the net head. The net head we can calculate after we get the gross head and the loss in friction. So 510 minus 170, we get 350 meters. And then the flow rate, Q equal 2.2 meter cube per second, angle of deflection phi equal to 165 degrees, and velocity coefficient CV equal to 1.0, speed ratio Ku equal to 0.45, and water density equal to 1000 kg per meter cube. Next, before we go further, we also can calculate friction loss using this Darcy equation, which is equal to 4FLV squared over D2G. But in our case here, we just use the one-third, the information that given in the question, which is head loss in friction is one-third of the gross head. Right, next, we look into the bucket of the Pelton wheel, and we know that the water coming from the jet will hit the splitter at the center of the bucket and divide the stream into two streams. All right. So we look into the first is the V1, or the velocity at the inlet of the bucket, and we know that for Pelton wheel V1 is equal to VW1, and then U1, which is the velocity of the bucket, and VR1, the relative velocity experienced by the bucket. And at the outlet, is VR2 come out from the bucket with angle of deflection phi equal 165 degrees, and V2 U2, which is equal U1, and VW2 and VF2, and the angle between V2 and VW2 is alpha 1, and the angle between VR2 and U2 is beta 1, also known as the blade angle. Okay, velocity triangle is very important, so keep on practicing sketching velocity triangle every time you solve concern problem. All right, next, the blade of angle beta 2 we can calculate from angle of deflection, which is beta 2 equal 180 degrees minus phi, which is minus 165. So beta 2 is equal to 15 degrees. All right. Our second task in this question is to determine the hydraulic efficiency of the Pelton wheel. We know that hydraulic efficiency of a Pelton wheel can be calculated using this expression, which is equal to 2 VW1 plus VW2 multiplied by U divided by V1 squared. If we look into this expression, we know that we already have all information that are needed to calculate hydraulic efficiency. So we just simply plug in all those values inside this equation, and we will get the hydraulic efficiency of the Pelton turbine in our case here is equal to 0.973, or in terms of percentage equal to 97.3%. Alternatively, we also can calculate hydraulic efficiency using this expression, which is equal to VW1 plus VW2 multiplied by U divided by GH. So this equation or this alternative equation might be useful in some other cases that we might not be able to calculate hydraulic efficiency using the first hydraulic efficiency expression we show here. So now we have completed our task in this example 1. First, to calculate the power developed at the runner, and to calculate the hydraulic efficiency of the Pelton wheel. As you can see, it's not that difficult. You just need to do it step by step. Let's take a look at another example. Two jets strike the bucket of a Pelton wheel which is having a shaft power of 15,450 kilowatt. The diameter of each jet is given as 200 millimeters. If the net height on the turbine is 400 meters, determine the overall efficiency of the turbine. Take CV equal 1.0. As usual, first of all, we highlight the information that we can extract from the question. First one is shaft power, which is equal to 15,450 kilowatt. And then the diameter of the jet is 200 millimeters. And then the net height is equal to 400 meters. And then we write down all those information. Number of jet NJ equal to 2, shaft power PS equal to 15,450 kilowatt, jet diameter DJ equal to 200 millimeters, net height H equal to 400 meter, and velocity coefficient CV equal to 1.0. So we need to calculate the overall efficiency. So let's take a look at the expression for overall efficiency. It's actually equal to the hydraulic efficiency multiplied by the mechanical efficiency equal to power at shaft over power developed at the runner. So we already know the power, the shaft power is given in the question is equal to 15,450 kilowatts, but we don't know the power developed at the runner, so we have to calculate this one. So we know that the power developed at the runner can be calculated using this expression rho GQH. And we look into the first term in this equation. Rho is not given in the question. If rho is not given in the question, we know that water, we can take the value of rho for water, or the density of water, as 1000 kilogram per meter cube. And then gravity, we all know gravity 9.81. and Q the flow rate. We don't have flow rate, so we have to calculate flow rate. And the net height is given in the question, which is equal to 400 meters. So we calculate the flow rate using the total flow rate by two jets. Okay, that's why AV will give you flow rate, but we have two jets, so we have to multiply the flow rate with 2. So Q, in this case, the total flow rate will equal to 2AV1. A is the area of the jet, can be simply calculated by pi over 4 dj squared. So we have dj value, we plug in this equation, we will get A is equal to 0.0314 meter squared. And then V1 we can calculate using CV square root of 2GH. We plug in those, we have the net height, so we the gravity and CV, so you will get V1 is equal to 88.58 meter per second. So we can calculate Q now. Q equal to 2 times the area 0.0314 times the velocity 88.58 equal to 5.56 meter cube per second. So now we can calculate the power developed at the runner. We have rho equal to 1000, G 9.81, Q 5.56, and the net height equal to 400. We multiply all of these values, we will get the power developed at the runner is equal to 21,817.44 kilowatt. And the overall efficiency will be the power at the shaft, which is 15,450 kilowatt, divide by 21,817.44 kilowatts, equal to 0.708, or in terms of percentage, it's equal to 70.8%. So we solve example number two without even need to draw or to sketch velocity triangles. So this type of question is just purely analysis by calculation. Thank you for your time. I hope now you have some idea on how to apply those equations, some of equations that we have learned in our previous lecture series. So see you next time. If you have any suggestion for improvement, please do get in touch. Bye bye.